In this video, we'll learn about the relational model. The relational model is more than 35 years old, and it's really the foundation of database management systems. It spawned a many billion-dollar industry. The relational model underlies all commercial database systems at this point in time. It's actually an extremely simple model, and that's one of its benefits. Furthermore, it can be queried. By that I mean we can ask questions of databases in the model using high-level languages. High-level languages are simple yet extremely expressive for asking questions over the database. And finally, very importantly, there are extremely efficient implementations of the relational model and of the query languages on that model. So let's move ahead and understand the basic constructs in the relational model. So the primary construct is, in fact, the relation. A database consists of a set of relations, or sometimes referred to as tables, each of which has a name. So we're going to use two relations in our example. And our example is going to be a fictitious database about students applying to colleges. For now, we're just going to look at the students in colleges themselves. So we're going to have two tables, and let's call those tables the student table and the college table. Now, as an aside, there's a healthy debate in the database world about whether tables, relations, ought to be named using the singular or the plural. I personally don't have a stake in that debate. I'm going to use the singular. Next, we have the concept of attributes. So every relation in a relational database has a predefined set of columns or attributes, each of which has a name. So for our student table, let's say that each student is going to have an ID, a name, a GPA, and a photo. And for our college table, let's say that every college is going to have a name, a state, and an enrollment. We'll just abbreviate that ENR. So those are the labeled columns. Now, the actual data itself is stored in what are called the tuples, or the rows, in the tables. So let's put a couple of data tuples in our tables. So let's start with the students, and let's say that our first student has ID 123, name is Amy, GPA 3.9, and she's happy with that, so she has a smiley photo. And our second student is 234, it's Bob. His GPA is 3.4. He's not quite as happy. And typically, of course, a table will have thousands, maybe millions, even sometimes billions of rows, each row containing a value for each attribute. In our college table, let's suppose we have, well, of course, we're going to start with Stanford in the state of California, and Stanford's enrollment is 15,000. We'll include our Cross-Bay rival Berkeley, again in the state of California. And Berkeley's enrollment is a whopping 36,000. And last of all, we are going to not be West Coast biased. We'll include MIT in the state of Massachusetts with an enrollment of 10,000. Now, of course, there's going to be, again, many more tuples in the college table and many more tuples in the student table. Okay, next, let me mention that in a relational database, typically each attribute or column has a type, sometimes referred to as a domain. For example, the ID might be an integer, the name might be a string, GPA might be a float, photo might be a JPEG file. We do also, in most relational databases, have a concept of enumerated domain. So, for example, the state might be an enumerated domain for the 50 abbreviations for states. Now, it's typical for relational databases to have just atomic types in their attributes, as we have here, but many database systems do also support structured types inside attributes. Okay. A little bit more terminology. The schema of a database is the structure of the relation. So the schema includes the name of the relation and the attributes of the relation and the types of those attributes, where the instance is the actual contents of the table at a given point in time. So typically you set up the schema in advance, then the instances of the data will change over time. Now, I mentioned that most columns have types, but there's also a special value that's in any type of any column, and that's a special value known as null. And nulls are actually quite important in relational databases. Null values are used to denote that a particular value is maybe unknown or undefined. And so let's add another tuple to our database, let's say 345, another student named Craig, and for whatever reason Craig doesn't have a GPA. Maybe Craig is homeschooled, maybe Craig doesn't want to reveal his GPA. So then the database would contain a null value for Craig, and we'll just put a neutral face there. Or, for example, maybe Bob doesn't want to have his photo in the database, so then Bob would have a null value for his photo. So again, nulls can go anywhere. Now, null values are useful, but one has to be very careful in a database system when you run queries over relations that have null values. In a later video, we'll go into this in more detail, but I just wanted to give a sort of example of what can happen. So let's suppose we're asking a query over our student table of all students whose GPA is greater than 3.5. So when we run that query on our database, obviously we'll get Amy out. Obviously we won't get Bob out, but should we get Craig? The answer is no. We don't know for a fact that Craig's GPA is greater than 3.5. So we'll only get one student out from that query. Now let's suppose we had another query where we're going to ask for the GPA less than or equal to 3.5. So similarly, well, we would not have Amy in the result, and we would certainly have Bob in the result. And similarly, we would not have Craig in the result because we don't know that his GPA is less than or equal to 3.5. So far, so good. What it gets a little weird is when we add an or here in our query. And we say, I want everyone whose GPA is greater than 3.5 or whose GPA is less than or equal to 3.5. And even though it looks like every tuple should satisfy this condition, that it's always true, that's not the case when we have null values. So that's why one has to be careful when one uses null values in relational databases. Let me erase this now, and let's move on to our next concept, which is the concept of key. Key is, again, another important concept in relational databases, and a key is an attribute of a relation where every value for that attribute is unique. So if we look at the student relation, we can feel pretty confident that the ID is going to be a key. In other words, every tuple is going to have a unique value for ID. Thinking about the college relation, it's a little less clear. We might be tempted to say that the name of the college is an ID, but actually college names probably are not unique across the country. There's probably a lot of, or several colleges named Washington College, for example. You know what? We're allowed to have sets of attributes that are unique, and that makes sense in the college relation. Most likely the combination of the name and state of a college is unique, and that's what we would identify as the key for the college relation. Now, you might wonder why it's even important to have attributes that are identified as keys. There's actually several uses for them. One of them is just to identify specific tuples. So if you want to run a query to get a specific tuple out of the database, you would do that by asking for that tuple by its key. And related to that, database systems, for efficiency, tend to build special index structures or store the database in a particular way so it's very fast to find a tuple based on its key. And lastly, if one relation in a relational database wants to refer to tuples of another, there's no concept of pointer in relational databases. Therefore, the first relation will typically refer to a tuple in the second relation by its unique key. As our videos develop, we'll see the importance of keys. Okay, just to wrap up, I'll mention how one creates relations or tables in the SQL language. It's very simple. You just say create table, give the name of the relation and a list of the attributes. And if you want to give types for the attributes, it's similar except you follow each attribute name with its type. So to wrap up, the relational model has been around a long time, has started a huge industry. It's used by all database systems. As you've seen, it's a very simple model, and we'll shortly see that it can be queried with very nice languages, and finally, it's been implemented very efficiently. In this video, we're going to learn about querying relational databases. We're not going to focus on a specific query language. We'll do that later. We're just going to talk about querying relational databases in general. Let's start by talking about the basic steps in creating and using a relational database. So, by the way, I should mention that database people have this habit of drawing databases and database systems as gigantic disks, so I'll be using that same habit. So the first step is to design the schema of the database and then create the schema using a data definition language. So as we discussed in previous videos, in a relational database, the schema consists of the structure of the relations and the attributes of those relations. So we set those up inside our big disk. Once that's ready, the next step is to load up the database with the initial data. So it's fairly common for the database to be initially loaded from data that comes from an outside source. Maybe the data is just stored in files of some type, and then that data could be loaded into the database. Once the data is loaded, then we have a bunch of tuples in our relation. Now we're ready for the fun part, which is to query and modify the data. And so that happens continuously over time as long as the database is in existence. So let's just say for now that we're going to have human users that are directly querying the database. In reality, that typically happens through, say, an application or a website. So a user will come along and we'll ask a question of the database and we'll get an answer. Might come along and ask another question, Q2, and get another answer back. The same human, or maybe a different human, might ask to modify the database, so they might want to insert new data or update some of the data. The database will come back and say, okay, I made that change for you. So that's the basic paradigm of querying and updating relational databases. Relational databases support ad hoc queries in high-level languages. By ad hoc, I mean that you can pose queries that you didn't think of in advance. So it's not necessary to write long programs for specific queries. Rather, the language can be used to pose a query as you think about what you want to ask. And as mentioned in previous videos, the languages supported by relational systems are high level, meaning you can write in a fairly compact fashion rather complicated queries, and you don't have to write the algorithms that get the data out of the database. So let's look at an example of a few queries. Let's go again to our imaginary database of students who are applying to colleges, and here's just 3 examples of the types of things that you might ask of a relational database. You might want to get all students whose GPA is greater than 3.7 who are applying to Stanford and MIT only. You might want to get all engineering departments in California with fewer than 500 applicants. Or you might ask for the college with the highest average accept rate over the last 5 years. Now, these may seem like fairly complicated queries, but all of these can be written in a few lines in, say, the SQL language or a pretty simple expression in relational algebra. So some queries are easier to pose than others. That's certainly true. The 3 queries you see here are, as I said, pretty easy to pose. Now, some queries are easier for the database system to execute efficiently than others, and interestingly, it's not necessarily these 2 things aren't necessarily correlated. There are some queries that are easy to pose but hard to execute efficiently, and some that are vice versa. Now, just a bit about terminology. It's frequently people talk about the query language of the database system. That's usually used sort of synonymously with the DML or data manipulation language, which usually includes not only querying but also data modifications. In all relational query languages, when you ask a query over a set of relations, you get a relation as a result. So let's run a query Q, say over these 3 relations we've shown here, and what we'll get back is another relation. When you get back the same type of object that you queried, that's known as closure of a language, and it really is a nice feature. For example, when I want to run another query, say Q2, that query could be posed over the answer of my first query and could even combine that answer with some of the existing relations in the database. That's known as compositionality, the ability to run a query over the result of a previous query. Now let me talk briefly about 2 query languages. We'll be learning these languages in detail later, but I'm just going to give the basic flavor of the languages here. Relational algebra is a formal language. Well, it's an algebra, as you can tell by its name. So it's very theoretically well-grounded. SQL, by contrast, is what I'll call an actual language or an implemented language. That's the one you're going to run on an actual deployed database application. But the SQL language does have as its foundation relational algebra. That's how the semantics of the SQL language are defined. Now, let me just give you a flavor of these 2 languages, and I'm going to write 1 query in each of the 2 languages. So let me get rid of this little line here. Let's start in relational algebra. So we're looking for the IDs of students whose GPA is greater than 3.7 and they've applied to Stanford. In relational algebra, the basic operators of the language are Greek symbols. Again, we'll learn the details later, but this particular expression would be written with a pi followed by a sigma. The pi says we're going to get the ID. The sigma says we want students whose GPA is greater than 3.7, and the college that the students have applied to is Stanford. And then that will operate on what's called the natural join of the student relation with the apply relation. Again, we'll learn the details of that in a later video. Now here's the same query in SQL, and this is something that you would actually run on a deployed database system, and the SQL query is in fact directly equivalent to the relational algebra query. Now, pedagogically, I would highly recommend that you learn the relational algebra by watching the relational algebra videos before you move on to the SQL videos. But I'm not going to absolutely require that. So if you're in a big hurry to learn SQL right away, you may move ahead to the SQL videos. If you're interested in the formal foundations and a deeper understanding, I recommend moving next to the relational algebra videos.